just give you some of the key ideas that the committee has developed for modernizing probable maximum precipitation. And moving on to the next slide, the place we'd like to begin is to just highlight some of the key take-home messages from the study. The first point to emphasize is that probable maximum precipitation is important, and the second is that major changes are needed to probable maximum precipitation to assure the safety of high-hazard infrastructure in the U.S., in particular dams and nuclear power plants. Arguably, the most important recommendation of the committee is to pursue an approach for estimating probable maximum precipitation that's based on climate model simulations. And this is what we refer to as model-based PMP estimation. This recommendation is the key to addressing the challenges of climate change and for providing quantitative assessments of uncertainty in PMP estimates. And a recurring theme throughout the study is that climate change and uncertainty characterization are two of the biggest challenges for assuring infrastructure safety over the coming decades. Now, the committee notes that model-based PMP estimation has advantages, significant advantages for computing probable maximum flood relative to conventional procedures. Now, probable maximum flood was not within the task that the committee was asked to address, but we do detail the advantages of model-based PMP estimation for computing probable maximum flood. A major recommendation is centers on a new definition of probable maximum precipitation, which is based on annual exceedance probabilities and not on upper bounds of rainfall. This recommendation is grounded in assessments of the scientific evidence for the existence of bounds on rainfall and assessments of the statistical problem of estimating bounds. And the committee concluded that a new definition of probable maximum precipitation is essential for modernizing PMP. Model-based PMP estimation, it's an ambitious goal and it will take time to achieve. And so the committee recommends a phased approach with near-term enhancements leading to model-based PMP estimation. So these are core recommendations. And Jonathan, if you move to the next slide, these core recommendations reflect our vision for modernizing PMP. Sort of in a nutshell, model-based PMP estimation is ambitious, but it's achievable. And a critical point to note is that the advances that are needed for model-based PMP estimation will contribute to a number of other high-profile societal problems that are associated with climate extremes. So modernizing PMP, the impacts will extend well beyond the PMP context per se. Next slide, Jonathan. Now, the committee had a number of review and assess tasks, and these are detailed in the report, but what we'd like to focus on is the fourth task, which is to recommend an approach for PMP estimation that explicitly incorporates the effects of climate change and quantitative assessment of uncertainty in PMP estimates. And this recommendation is envisioned as providing a national standard for PMP estimation. Next slide. It turns out that that's a pretty challenging task. The Academy assembled just an outstanding team with the committee members with the expertise required to address the topic. We held a number of information gathering sessions. The final report also benefited significantly from contributions from reviewer comments. And so the final report reflects contributions from a broad segment of the community that's interested and involved in probable maximum precipitation. So next slide. Just briefly, probable maximum precipitation is defined as an upper bound on rainfall. PMP is estimated based on data, and it's data from storm catalogs of extreme rainfall events. A key feature is that these storm catalogs are incomplete, both in terms of their temporal representation of extreme storms and their spatial representation of extreme storms. It's an engineering design and safety standard for high hazard dams and for nuclear power plants. And then the most basic thing to keep in mind is that PMP methods are old, more than 80 years, and the heritage extending back to the origins of the Miami Conservancy in the 19-teens. The figure shows the locations of the more than 16,000 high hazard dams in the US, illustrating the one element of the nature of the problem associated with PMP estimation. And so in addition to this, more than 50 nuclear power plants for which PMP is essential. Next slide. We took a close look at stakeholders for modernizing PMP, and then the sort of broader audience and stakeholders include the regulatory agencies. It includes dam owners and operators, federal agencies like NOAA that are involved in development of PMP procedures, and the private engineering community that's been involved in PMP studies over the last several decades. And then this broader audience relates to this notion that the PMP report and the methods used for PMP estimation will have much broader impacts on problems dealing with climate extremes in a warming climate. Next slide. A synthesis of the major weaknesses of current PMP technology. The assumption that rainfall is bounded being at or close to the top of the list, the absence of procedures for dealing with climate change, the incomplete nature of storm catalogs, important for a number of reasons, but going to the bottom, it precludes any capability for quantifying uncertainty in PMP estimates. And then there are a collection of PMP methods for which there is weak scientific grounding, storm transposition, moisture maximization, and the procedures that are used in practice to deal with the effects of orographic precipitation. So these are key weaknesses in PMP estimation. Next slide, Jonathan. And they're translate to our recommended new definition of probable maximum precipitation, which is, as I noted, grounded in annual exceedance probabilities and not in upper bounds on rainfall. I will emphasize that the committee delved deeply into the question of bounds on rainfall and concluded both from a first principles scientific perspective, as well as from the existing evidence from observations, the assumption of bounds on rainfall is not a tenable foundation for modernizing probable maximum precipitation. Now, I point to a key recommendation, and that is the community effort that will be required to develop the procedures used for specifying annual exceedance probabilities that define probable maximum precipitation. So that'll be a key element. The report details some of the key information. I'll have a few more words to say about that in a few minutes. So the new definition is one of the key ingredients. Jonathan, next slide. And it's grounded in this recommendation for a phased approach, and recommendation 5.1 lays out the phased approach for probable maximum precipitation estimation with near-term enhancements to existing procedures leading to model-based PMP estimation. And figure 5-1, it's a roadmap. It shows how the diverse recommendations or the key recommendations tie together. There's a timeline from current practice to near-term enhancements within 5 years and model-based PMP estimation in 10 to 15 years. I will note a key element is the model evaluation project, which both determines when model-based estimation is fit for purpose and provides key scientific information for near-term enhancements. So now just a couple of looks at the green right-hand side on model-based PMP estimation. So Jonathan, the next slide. The sort of the core notion is that long simulations, high-resolution climate models will provide the observational foundation for PMP estimation. So that's the core of model-based PMP estimation. This capability of producing long simulations that accurately reproduce the climatology of PMP magnitude rainfall. And the paired notion, Jonathan, if you go to the next slide, is that gives us effectively large sample sizes, and we recommend extreme value analysis methods for both estimating probable maximum precipitation and for estimating uncertainty of the PMP estimates. So we have the model-based PMP estimation, the climate model simulations, and then we have a key statistical component. And implementing model-based PMP estimation will certainly require major contributions from the statistical community. So those are core elements of model-based PMP estimation. And stepping back in time, Jonathan, if we can go to the next slide, the near-term enhancements over the next 5 years have 3 components. The first is data enhancements. Digitizing the existing storm catalog is important. Probably the most critical element is effectively using rainfall fields derived from the National Radar Network, so that extends back to the early 1990s, and nearly complete records for the US beginning around 2000. And then the committee also envisions an important role for model reconstructions of major historical events. So those are the 3 components to data enhancements. Now, scientific guidance deals with these principally with these 3 tasks: storm transposition, moisture maximization, and orographic transposition factors. The report details the scientific weaknesses, and in developing model-based approaches for PMP estimation, one of the key paired advantages will be providing the scientific guidance for near-term enhancements to probable maximum precipitation. Now, there's a third component, Jonathan, if you can step to the next slide. Climate change is so important that even for near-term enhancements, it's critical to provide tools for reflecting the potential changes in probable maximum precipitation. And so we recommend model-based scaling relationships between extreme precipitation and temperature. Now, ultimately, model-based PMP estimation provides the sort of key resources for effectively dealing with climate change. But we do see in near-term enhancements a requirement for providing guidance on climate change impacts. And next slide, which deals with the model evaluation project, a key element, it serves 2 fundamental purposes. One fundamental purpose is to develop the modeling infrastructure that allows the vision for model-based PMP estimation to be implemented. And sort of paired with that is the decision framework for deciding when model-based PMP estimation is fit for purpose. As I mentioned, the elements that are involved in the model evaluation project will provide the scientific foundation for near-term enhancements to probable maximum precipitation. The radar-based data sets that will be a key element of near-term enhancements data element will provide key data resources for the model evaluation project. So we want to emphasize that we see close interactions between near-term enhancements and model-based and the model evaluation project providing the central framework for addressing the key challenges. And then, Jonathan, next slide. Back to the, the vision is that model-based PMP estimation can be achieved, and it can be achieved in a time frame that is important for modernizing PMP. But again, we want to emphasize that the path to modernizing PMP will have major impacts on a wide array of problems that deal with climate extremes. Final slide, Jonathan. An outstanding committee. I'd like to thank all of the committee members and particularly thank Stephen and Jonathan for their leadership within the Academy. With that, let's open the floor for questions.
All right, that sounds good. As I said before, just raise your hand. Oh, Bilal.
Yeah, first of all, thank you so much for the presentation. This is timely, and I'm looking at the definition, which is most significant. I'll say it's basically there is time and space. I think I have good handle in terms of the definition when it comes to the time. It's particular duration. You could specify the climate period, and we are interested in an annual probability of exceedance. Now, for the spatial aspects of it, it's unclear to me because the depth is going to vary spatially, and you have there the location and the areal extent. So when we have the exceedance, the depth, is it defined as, and I'm interested in the exceedance probability of the depth, is it defined in terms of the average over the area, or is it because it's going to have variation spatially? And what about non-stationarity in the spatial aspect of it? At the very end, we are dealing with the drainage basin, so maybe the yield of that drainage basin is most important. So I have these questions about the space aspect. Thank you.
Yeah, they're great questions, and they are at the core of why model-based PMP estimation has advantages over conventional methods. And the most basic reason is that you can do the analyses for drainage basins. Whereas conventional approaches to PMP estimation, you estimate PMP for a particular area, not directly tied to a drainage basin. For model-based PMP estimation, we can tailor analyses. We can have rainfall analyses that are structured for drainage basins. Now, there's other information, so you can talk about the 6-hour PMP for a drainage basin that is 100 square miles in drainage area. But for model-based PMP estimation, you also have the things that you were alluding to. You can have spatial structure of the rainfall over the 100 square kilometer watershed, and you can have time distribution of the rainfall. So these are elements that are challenging with current PMP methods, and they are elements for which model-based PMP estimation opens vistas for getting at what we really need, the PMF and the sort of associated characterizations of uncertainty. I know other committee members probably have thoughts on that. It's a really key question. John, I see, you look like you have a comment there.
Hi, Effie,
Go ahead,
go
John.
ahead. John England. So there's two hints. We try to be flexible in the report. So there's a lot of flexibility for NOAA and the partner agency, ASC, everyone here. So the hints I would point you to is figure 5.2. We try to illustrate what a distribution looks like in an application over a drainage basin. That's on page 96. And there's a subsequent figure later in the report in chapter 5.4, which sort of illustrates the products. And it's sort of hard because we're doing time slices, right? But at least it gives an idea that you can do applications on a CONUS wide basis, and they can be at very, very fine time in spatial scales to help hopefully answer that question. On the climate period though, we're also pretty flexible on, that's a decision framework on the period you choose, and models can provide those changes directly in their output using the ideas in chapter 3, whether you use a time slice that's say from 2040, 2100, or those sorts of ideas to bring those things in.
Thanks, John.
In fact, the figure 5.2 is very, very helpful. You have the word on the vertical axis, basin average, 96-hour precipitation. And I was wondering in the main definition, why the word average was not used. I mean, actually, that was what was in my mind. And I thought, well, maybe not having the word average will leave room for flexibility.
I mean,
Yeah, go
okay.
ahead, Evie.
This is a very basic question, Bilal. That's, I think, at the core of revising. So if you imagine your basin that you have interest or with the shape that it has, elongated or flat or whatever, et cetera, and we have built confidence in the model representation of the extremes in a period. You talked about non-stationarity. That's why we say within a climate period, because if things change, in the next 50 years, we're going to run new models. And you imagine that this basin, with its particular shape, particular area, and so forth, orientation, et cetera, is subjected to storms with different spatial structure, exactly, an ensemble of the storms, that every one of them will have, of course, climatologically similar, different in Florida, different in Seattle, but there will be an ensemble of them. I mean, sampling all the possible spatial temporal structures of the storms. Now, the end product would be that the area, the average that we're talking about will be the one that is captured by the basin, the specific basin. The time concentration is irrelevant because we're going to run all the storms through rainfall runoff modeling for PMF. So I think your questions, which are very basic, are addressed by the model-based PMP, the ensemble, production of storms with all their characteristics, which are space, time, variability, and so forth, structures, and running the storms through a rainfall runoff model will produce for the specific basin the design flood. I mean, I don't know if I said more than what John and Jim said, but this is at the core, I think, and you just hit it right. But I hope.
I have one follow-up, just a final one. So if you are looking at ensemble and it's the average, why the average? Why shouldn't be from the ensemble some percentile? Could be exceedance of the ensemble for an I mean, the vertical axis in figure 5.2a, which it has the word average. Average does
Yeah.
not appear in the definition. So somebody could choose something else than the average.
Yeah, you could. What is envisioned is that it is the average. And so you would have a 6-hour, 100 square kilometer PMP. And now it may be a 100 square kilometer drainage basin, not some arbitrary geometric shape. But you would have basin average rainfall, say annual maxima over that watershed, 6-hour time scale. You would have long records of that, and you would do extreme value analysis on long samples of annual maxima, 6-hour, 100 square kilometer average rainfall. And so that is in line with what conventional PMP estimates provide. It is, as we've emphasized, there is much more that you can bring with that. But the PMP estimate will still be for the average rainfall over 100 square kilometer watershed in that example.
Thank you.
I want to add two things. If we have a broad audience here, back to figure 5.2, we also tried with the statistics side to describe the uncertainty. So in figure 5.2, you'll see a red line and a blue line if you have it on your screen. So to Bilal's points, these are really important questions that should be addressed with recommendation 5.2 on the AEP ranges. So besides AEP, we tried to sketch out the green lines, which are the uncertainties for the probability for a given depth, as well as for the depth given a fixed probability. So those are things that should be addressed on that recommendation. On the scale issue, there's some background information in chapter 2, one in particular, just for this committee, because many people are focused on buildings, right, or things in the floodplain. We took a figure from it may have been an Oak Ridge report that she worked on, or somebody else. It sketches a nuclear reactor, essentially 1 square mile. Sorry, I forget the figure number. It's in the section on storm area sizes. And so getting to 1 square mile is a really big deal, right? And sometimes your applications may be at a finer scale than that. Models can help with that, and there may be some simplifications for products that if users are really at that very, very fine scale, like I want to know the rain pluvial depth at this building, FEMA considerations, which are important. Those things we thought about, and they're sort of tucked in there. And this committee could really help on some, product recommendations for that. Thanks.
One other point following on John's observations about scale is that of those 16,000 plus high hazard dams in the US, more than half are in watersheds that are smaller than 10 square kilometers. And so the problem of short duration, small area PMP estimation is critical, and it's where we have some of the greatest challenges, both for near-term enhancements because of the observational problems and model-based PMP estimates because we're looking quite often at extreme convective rainfall, which is going to be a challenge. But keeping in mind that small area, short duration is really one of the key problem areas for addressing high hazard structures in the US. John mentioned the nuclear power plants as another example of that.
Do we have other questions? If you're not familiar with the interface, if you go to reactions, it gives you the option to raise your hand. I guess then I have a couple. First of all, Joe, go ahead. I was looking for you, Joe, so.
I was at a doctor's appointment earlier, so I just got here. But I saw most of the presentation. I first of all, I want to, commend you all. I mean, I've not completely read every word of the report, but I thought the report was quite excellent, particularly like the staged approach. And also, for those who don't know, there's a wonderful historical summary of the concepts in this. I mean, it's not just your basic report, it's really beautifully written. The question I had, you have a timeline going out to the model-based PMP, the full model-based PMP, which involves, kilometer scale model, multiple ensembles of kilometer scale runs and evaluation process that goes out something like 10 years. I don't know what you were thinking for that timeline, maybe 10 plus, given the way things happen. By that time, we'll have realized close to 2 degrees of global warming. And the one thing I didn't see was an emphasis on attribution and using the trends that we will have seen, by that time, as a way to actually constrain the statistics. And I was actually hoping to see more of that because, current estimates are that we're heading for 2.7 degrees-ish, 2.73 degrees Celsius under current policy. So we'll be 2/3 the way there. So any comment on, the role for that in your model evaluation component?
Yeah, no, absolutely critical. One of the things that is briefly noted and probably not emphasized as much as it should be is that the observational base that we'll use for near-term enhancements is also one for developing model-based PMP estimation, but it also is a critical resource for examining the short-term changes in precipitation extremes. And being able to assess over the period from, say, 2000 to 2025, what the evidence is for changes in rainfall extremes is going to be one of the key ingredients, especially as we think about our approaches for temperature scaling relationships for the near term climate change assessments for PMP. The data side will play an important role in near-term enhancements, in developing the models, and in providing the capability for characterizing the changes over multiple decades.
Yeah, I mean, in particular, I was thinking about the geographical distribution because climate models and even high-resolution climate models, unfortunately, have a fair amount of geographical bias due to, in my view, the tropical Pacific and other large-scale errors. And they're not huge on a global scale, but they are significant on a continental scale. So using the observational trends, not just the mean values, regional observational trends, I think is going to be really, really powerful. And it sounds like there's room for that, even though it wasn't emphasized in the report. So that's good to hear.
Yeah, absolutely. Thanks.
Other questions? I guess I'm intrigued by the implications of first of all, I have not read the report, full transparency. But I am intrigued by the implications that the report has for other aspects of precipitation estimation. Does the study get into things, when we're talking about mid-century, end of century, does the report comment or get involved in, for example, scenario selection, model culling, model selection? Are those issues addressed in the report?
Yeah, we summarize the existing literature, but we don't. There's certainly not a specification of scenarios that should guide analyses, but it is an element that we examined and included in the report. Obi, do you have any other thoughts on the scenarios or other questions? I think you're still muted.
Yeah, no, I think, Ben, that's a good question. I think that was not one of our primary tasks to provide guidance on what scenarios, but with the advancement in science over the next 10 years, we'll have a better selections of what scenarios we should be using. The nice thing about the model-based approach is you will have simulations for the several scenarios you might want to look at, and so.
All right. No, that's helpful. Thank you.
In chat, Bilal has a question.
Bilal, do you have a question?
Yes, I was asking about the area reduction method or factor and the nature of its non-stationarity and how would we account for
Let's see. Can you,
Yeah, let me maybe try that. I think by having these high resolution model simulations, I think we'll have enough information on the spatial structure that we can look at to understand the non-stationarity of the areal reduction factor, which we didn't have in the current approach. So I think that having those simulations, long-term simulation, you'll have enough, basically realizations that we can look at to understand the areal reduction factor and its non-stationarity.
Yeah, and I want to add that it should be clear by now that we have been struggling by how limited the data are. Although I think conventionally we derive everything based on data, but we have come to a point and realize that the current data is not sufficient to derive something so extreme like PNP. So like as Obey said, a model in this particular case can provide very useful information for us to help for us to better understand this error reduction factor and also other things.
Yeah. Can I add that this is very critical because there is some modeling evidence that the footprint of storms is larger, gets larger under a warmer climate, particularly tropical cyclones. And I think that's directly relevant to Bilal's question about area scaling. If the footprints of storms are larger, then your scaling factors, so even scaling factors themselves may not be, static scaling factors are not the appropriate approach then at that point.
And my comment is that I think there's a possibility, but again, we have so limited data. I mean, so far, I think the most surprising one is Hurricane Harvey because it demonstrated that, yeah, you can see a large scale storm exceeding PNP at that level. But so far we only have that sample layer, and I'm just questioning. I think we're challenged by that how limited data they are. Yeah.
Kelly, at one point you had your hand up. Did you take it back down? Did you have a comment?
I'm trying to say really little, so if there's more questions, I can come in at the end. Yeah, keep letting this play out. Thanks.
Okay, Kelly, just be warned, I am going to come back to you at one point.
Okay.
Sihan?
Thanks, Dan. I do have two questions. I quickly scanned through this report. It's a very great document, a lot of history and a lot of inspiring methodology there. There's two questions I didn't get a very clear understanding. One is there has been many occasions in a report mentioning a large number of ensembles, but it's really not very clear, defined is what is large, and what is the minimum that is needed. If the final ensemble average is interested in, and I'm just curious to cover the deep uncertainties from variety of modeling outputs. Is there a consensus on the minimum required ensembles people should use, so that your output is somewhat credible or somewhat have a high confidence? Would, let's say, would time ensembles of simulations be sufficient, or you would have to use 30, 50, or what is considered basically as a large ensembles is needed? That's the first question. The second one is in terms of the baseline periods used to derive the impacts. I came across one sentence somewhere, I couldn't recall, but it seems like it's a length of the historical periods is 30 years. I got that part. I'm just curious whether that 30 years is an evolving baseline period. See, if this year you have the model run, you have the assessment, you could go back from, let's say, 1986 to from there and 30 years up to around 2016 or something. But after another 5 years, with that baseline 30-year periods evolving as well, And with that period overlapping with the previous PMP estimate using the historic data, or should that baseline period the same length as the historical analysis, and what is the impact of that baseline periods?
Yeah, to take a quick pass at the first question, we looked at the sample size question both from the perspective of the statistical perspective and from the model requirements. And at some level, it's the statistical side that that drives things. What is the effective sample size that you need to estimate a specified annual exceedance probability for the North American monsoon climate of the southwestern U.S. versus the tropical cyclone climate of Texas, or the sort of diverse small area climate of the central U.S. And so there will be geographic and climatological differences in sample requirements. And so that's one of those places where moving forward, having statisticians involved is going to be important. There are a variety of ways of thinking about tackling the ensemble simulation to generate the sort of effective sample size. And we point to a number of existing studies and emerging technologies. We see a potential role, for example, for AI, and at least providing some tools for enhancing sample size, but we don't have a roadmap for how the large ensemble simulations play out. And in terms of the climate change question, one view is that the climate period is, you want to know what 2030 PMP is. Now you've got a 30-year period, and you may have a 30-year period, let's say 25-year period, 2000 to 2025, where you have an observational base, and you can look both at changes over time, and you can look at your capability of reproducing precipitation over that time period. But the climate period for PMP estimation is going to be one of the things that is determined in this community consensus. What is the form that we ultimately need the climate information? Do you need 2030 PMP? Do you need 2050 PMP? And so the machinery that we've laid out can work in a variety of ways, but it will be a community effort to dictate how best to structure those products.
Right, thanks, Jim.
Jihan, if I can add to that real quickly, if you look at figure 5-3, it shows the sort of gives you an idea about the number of years of sample size from a statistical point of view as a function of shape parameter. I guess something that John mentioned. And we also mentioned in the report that the potential for doing non-stationary modeling of extreme values, because we have long, ensemble simulations. So I think.
Oh, I think you froze, Obey.
Oh, all right.
No, you were getting right to the end there of your question.
No, I was done, Dan.
Oh, okay.
Thanks.
All right, thanks, Obey. All right, in the interest of time, I'm just gonna, Kelly, I know you followed this process, from your NOAA perspective. I know you're involved in the Atlas program and the development of IDF. I know you've been working with, some of the ASCE committees that are writing standards that will use IDF, for example. Is, from your perspective, are there some implications in this study that ASCE should be particularly focused on, or do you see it as being basically in concert with some of the approaches we've been exploring, for example, for rainfall IDF? I'm just curious. You've kind of got a unique position.
Yeah, thanks. Hold on a second, let me see. I'm screen sharing. Okay. I didn't know you were going to ask it that way. I'm going to turn it right back around at you.
You can change it any way you want.
Can you see this slide?
Yep.
Okay.
I see
so so full disclosure for people who don't know, I mean, NOAA sponsored this study. We knew we've been working with lots of folks in this community for a long time, and we knew that we didn't pretend to know how NOAA should just like set out and start this. So National Academy study was first on the list of how to proceed, and it worked out amazingly, as you guys all said. This is a fantastic report. And so what happens next? We have all of this was done with 5-year bipartisan infrastructure law money, and so we're about 2.5 years into that. And so what'll happen next on the NOAA end of things that we are already supported to do is, this is just kind of the timeline. We're still all digesting. Over the past 2.5 years, we've amassed a team of people who have a lot of exciting skill sets, but don't necessarily come from a community at all versed in PMP. So we're trying to digest the report and figure out how to make NOAA research goals aligned. So that's kind of like the next couple of months. In the fall is when we'll start talking about a little bit more openly an implementation strategy, and start passing that through our like main partners, which ASCE is one of them. And then I'm saying late fall, it's probably going to be winter of next year. We'll follow some of the practices that the Atlas 15 project has done in terms of hosting technical workshops to get more official like feedback on, here's what the report said, here's what we're thinking about, how does this suit X, Y, and Z. So just that's just more information. But to your point, to your question, we were in terms of ASCE, and especially coming out of the workshop a couple of weeks ago, some things that I wanted to bring up, or not even bring up, maybe just like leave us with, is I would like to better understand ASCE's role in establishing the new PMP definition. So if you recall, the recommendation 5.3 is to redefine PMP, which is fantastic from a science perspective. From like a procedural, bureaucratic perspective, I'll admit, makes my head spin. I know we can figure this out, but like doing this through the AMS, the ASCE, the ASDCO, and ASDSO, and all that stuff. So understanding ASCE's role in establishing a new definition, and then also establishing the AEP ranges, right? Like those are still an open question. So I think that's an area that we can look to. Ever since I kind of came into the ASCE NOAA world a year or two ago, I've been talking about PMP, but working mostly at, like we just said, like Dan said, on more IDF-based things, because I have this in my head that that's where ASCE cares most. But we're going to be moving more into that space. So how does this change in definition change ASCE interest kind of in the long term? And then maybe more pragmatically close term, so ASCE 728, the Future Conditions chapter, is going to be one of that, and NOAA Atlas 15 Volume 2 are going to be kind of the way that the community kind of first sees some of these future projection information. And from our stance within PMP, that's a huge benefit, because we get to learn what works well. And so kind of, I raised my hand earlier to kind of speak to the scenario questions. And so I've been following closely the talks about, adopting a global warming level framework. And so watching really closely like how that plays out with user communities, and being prepared to follow suit too. So there are a number of touch points, but I think like really broadly, the redefinition of PMP into more of an AEP space hopefully makes this far more relevant and kind of like central to things that ASCE and NOAA are talking about anyway. And yeah, so my questions are kind of back to the ASCE community, like how can this work? Where are the biggest interest points, and where should we kind of like focus for short and medium term goals? So that's answering a question with questions.
No, that's fine, Kelly. Any last questions or thoughts? Otherwise, I think we'll conclude this portion of the agenda. Jim, everyone, thank you so much for your work on the study. Thank you for joining us today. If we have some specific questions about the report, I'll direct those to Stephen and he can share as appropriate. Does that work? All right,
That
excellent.
sounds good.
Oh, John.
Yeah, can I
Last thought.
interject? Yeah, last thought. Well, it's really Ben D'Angelo's question here in the chat about the CMIP process. So I'd like to address this now because I've had some questions from my colleagues here at the core on, well, what are we doing and how is this integrating and stuff. So let me start with the committee did not fully, we left a lot to NOAA on this, so we didn't specifically address the CMIP process in chapter 3 and the new advances. There are pieces and parts in there. So this is more of a personal perspective. And I don't know if Dagmar is still on the phone here from the Bureau, but when I was at the Bureau, we worked with Kelly and Joe and things like that. So there's a CMIP process that had been worked for the basin studies that the Bureau of Reclamation did starting in the early to mid 2000s, where we did statistical downscaling, CMIP 3 scenarios, then we went to CMIP 5, right? So that technology has been in practice for a while, looking at water supply stuff. And we did some pilot studies on looking at precipitation frequency with that in the west and near the West Coast, particularly Friant Dam in California. So there's an opportunity for ASCE to really look at that, and with NOAA and everybody here on the call, right? We're now moved to dynamical models. We have CONUS 404 rolled out through NCAR. Like that technology has been literally used for, I would say, the past couple of decades. And now we could sort of try to combine this. So it's really opens the door to PMP, precipitation frequency, bringing together and the models to answer a whole bunch of questions for society, which are tied to extremes, whether they're droughts. I'm the flood guy, right? But that really, those processes surely could be considered and influence how ASC can do this and the community at large.
Thanks, John.